Okay, here we have 5 different inferences, each of which is valid. And let's go through each one using our natural deduction proof system to prove that it's valid. We'll start with this one here. So I will write down the premises first. Okay, and from these 2 premises, we want to derive there is an x LMX. Now, this proof's pretty straightforward. We're going to say, okay, we have this premise, there is an x ln x, n loves someone, as it were, and we're going to pick some arbitrary individual from the domain A and suppose that n loves A. And under that supposition, we're going to try to derive that there's someone that m loves, and then we can use existential elimination to get there is an x LMX back out into our original or home column of reasoning. And how can we get there is an x LMX? Well, we want to get something like LMA. And how can we get that? Well, we just use the first premise here that n is identical to m. So given that n loves A, we can, from those 2 formulas, automatically derive that m loves A. There we're just using the identity elimination rule. And so from here, it's just existential introduction to get there is an x LMX, and then existential elimination to get this formula back into the original column of reasoning. Okay, here's the next problem. We have as our first premise, no one loves themselves, and n loves someone, so therefore there's someone who isn't n that n loves. That makes sense. Let's try to write out the proof. So start by writing down the premises again. And this is the conclusion that we're trying to derive. And again, it makes sense to start by instantiating this existential statement, taking some arbitrary member from the domain and supposing that they are loved by n. And now under that supposition, we're going to try to derive this existential statement. And presumably we're going to get this existential statement by deriving the instance of it that says A is distinct from n and ln A. We already have the second conjunct here, ln A, so it's just a matter of proving that A can't be identical to n. And how are we going to get that A is distinct from n? Well, we're going to use this first premise that no one loves themselves, because if we supposed that A was identical to n, then that would mean that n loves themselves, which would mean someone loves themselves, which contradicts this. So we're just going to carry out that reasoning in our proof here, supposing that A is identical to n, which would mean, using the identity elimination rule, that n loves themselves. That's identity elimination, citing lines 4 and 3, substituting n in for A here, given that A and n are identical. And now from ln n, we can derive there is an x LXX just by existential introduction. And that contradicts the first premise, so we derive absurdity. And so that gets us the negation of what we suppose, that A is identical to n. So again, remember, this is just shorthand for the negation of A equals n. So we're just using reductio reasoning. And now we conjoin lines 8 and 3 and use existential introduction to get from line 9 to 10. And finally, having derived this formula here, we can use existential elimination to bring it back out here. Okay, here's our next problem. Let me write down the premises again and our conclusion, the target that we're headed for in this derivation. So here our premises say there's someone that N loves that does have the property F, is funny, say. And second premise says there's someone that N loves that fails to have that property that isn't funny. And so therefore there's an X and a Y such that N loves X and loves Y, and they're distinct. In other words, there are at least two people that N loves. That clearly follows, given that N loves a funny person and loves an unfunny person, then there have to be at least two individuals that N loves, because the same person can't be both funny and not funny. Now we just have to do the derivation. We've got two existentially quantified statements here at the start. So most likely strategy here is going to be to do two subproofs, one embedded within the other. Let's start by imagining this existential statement to be satisfied by some arbitrary individual from the domain. And now we're also going to suppose that this existential statement is satisfied. So we're going to start another subproof within this one. And crucially here, we have to, when we imagine who satisfies this statement, we have to pick somebody new to the proof. We're supposing Alex, say, satisfies this existential statement. We're supposing Alex is loved by N and is funny. When we pick someone to suppose is loved by N and not be funny, we have to pick someone new to the proof. So we'll have to do, say, LNB and not FB as the supposition at the start of our next subproof. This is a requirement of using the existential elimination rule, that the person you use to instantiate the existential has to be new to the proof. They can't have been mentioned at all prior to that point. So that's why we have to pick to B to instantiate the second existential, given that we picked A to instantiate the first one. Okay, now at the conclusion of this second subproof, we're going to want to derive the ultimate conclusion, and then we're going to use existential elimination to bring this back here once, and then existential elimination again to bring it back here. But for now, let's concentrate on getting it in here. We're going to want to derive something that we can use existential introduction on twice to get to this point. And presumably that's going to be LNA and LNB, and A is distinct from B. If we can derive that, then we can use existential introduction twice to get this. Now, we already have LNA as a conjunct here and LNB as a conjunct here, so it'll be easy to get those. We just need to get A is distinct from B. First, let's write down the two conjuncts that are easy to get, LNA and LNB. Now, to get A is distinct from B, well, we just use reductio reasoning, right? Suppose A were identical to B, well, then we would get a contradiction because we have FA and not FB. So if A were identical to B, we'd have the same thing being F and not F, which can't happen. So we're going to get A is distinct from B by supposing A is identical to B and getting a contradiction. Once I suppose A is identical to B, I can use FA. I can just use conjunction elimination to get FA in here. And now having A is identical to B and FA, identity elimination rule lets me swap B in for A here, getting FB. And now I'm running out of room a little bit, so let me just readjust the bottom of this proof so that I have a little more room. Okay, so now we've got to FB. We can derive not FB from this conjunction here just by conjunction elimination. And of course, from FB and not FB, we get absurdity, and then that gets us the negation of A equals B by reductio. Okay, so now we have these three conjuncts that we were going for that are part of this big conjunction here. So now it's just a matter of joining them together. Now we just use existential introduction twice to get to here. And finally, we just use existential elimination twice to get this conclusion back into our original column of reasoning. Okay, moving on to problem number 4 here. These are equivalent ways of saying that there is exactly one thing that is F. In the textbook, Smith shows how to derive this formula from this one. He leaves it as an exercise for how to derive this formula from this one. So to go from here to here. So we'll do that proof now. Start by writing down our premise. Okay, we're trying to derive this conclusion here. Okay, now to derive this conclusion, presumably we're going to start by instantiating this existential statement and then deriving this conclusion under that supposition and using existential elimination to bring this all the way back out. So let's outline our proof like that. And presumably we're going to get this formula here by using existential introduction on the formula Fa, and for all y, if Fy, then y equals A. Now, this formula itself here is a conjunction that's got Fa as one of the conjuncts, and then this universally quantified statement as the other conjunct. Presumably, we're going to get this formula by deriving these conjuncts separately and then putting them together. So we're going to want to get Fa and this on their own lines. So let's write down Fa, and for all y, Fy, then y equals A. And this presumably we're going to get by universal introduction on if FB, then B equals A. So now we've sort of reduced our problem to deriving these two formulas. And this is what we have to work with here. So this is a biconditional if and only if statement. Officially, we don't actually have this both-sided arrow in our formal language. We really just understand this as the abbreviation of a longer formula, which is the conjunction of two conditionals. Let's instantiate this universally quantified statement. From this, we can derive any instance of it, right? So we can derive FB if and only if B equals A. And this we understand to just be the conjunction of if FB, then B equals A, and if B equals A, then FB. So this formula here is really just a shorthand for this conjunction here. So we really have this conjunction at line 3. That's really the formula that we have there. So we could just use conjunction elimination from this to get this formula. What about getting Fa? Well, presumably we're going to want to get the instance of this formula that has Fa here. We're going to want to get Fa if and only if A equals A. Now this formula here, of course, is just shorthand for the conjunction of two conditionals. If Fa, then A equals A, and if A equals A, then Fa. And this second conditional here, if A equals A, then Fa, that's going to be super helpful in letting us derive Fa, because the antecedent A equals A, we can get that just using the identity introduction rule. So let's pull out this conjunct using conjunction elimination and then use identity introduction to get A equals A. Now that we have these two formulas, we can use modus ponens to get Fa. I wrote this formula first, so I'll just take care of that one first, so that we're just getting as the first conjunct of this conjunction here. So this would be line 7 being derived by conjunction elimination from line 3. FA is line 8 derived from line 6 and 5 using modus ponens. And then this is line 9. That's universal introduction on line 7. Right? Crucially, the name B does not appear in any live assumptions for this line. A appears in line 2, which is one of the live assumptions for line 7, but B does not appear in line 2 or line 1, which are all the live assumptions for this line. So we can universally generalize on B here. So that's why it's legitimate for us to get this from line 7 using universal introduction. Now we have FA, and for all y, if Fy, then y equals A. We can conjoin them to get line 10. And then it's just existential introduction on line 10 to get line 11. And then it's existential elimination on lines 1 and the subproof from 2 to 11 to get our final conclusion back into the home column. Okay, finally, let's tackle this last derivation here. So we've got our 3 premises and our conclusion. I'll start by writing down the premises and the conclusion that we're going for. So if we look at our premises and our conclusion, it always helps to sort of think about what our premises are saying and what our conclusion is saying, and just kind of think a little bit intuitively about why it would make sense that this conclusion follows from these premises. So here we've got a first premise that says there are at least 2 things that are F. And our second premise says there's something that's G. And our third premise, oops, I left out the negation sign there. That's important because our third premise says anything that's G is not F. So whatever this thing is that's G, it can't be one of these things that are F. We know there's at least 2 of them. And then we've got a thing that's G that's not F, so it's not one of those things. And our conclusion says, therefore, there are at least 3 things. There's an X, Y, and Z that are all distinct from each other. So that makes sense. From these premises, we should be able to derive this conclusion. Now, in terms of the actual mechanics of showing that in our proof system, we've got some existentially quantified statements here. The premise is a sort of doubly existentially quantified statement, as it were. So we're going to want 3 subproofs where we instantiate the there is an X, instantiate the there is a Y, and then a third subproof that instantiates there is an XGX. And we're going to want to make sure that we're using new individuals each time we instantiate an existential, someone that hasn't been mentioned in the proof so far, because that's a requirement of the existential elimination rule, which is what we're ultimately going to be relying on here. So we'll start with this first premise. Let's instantiate that and create a subproof where we say, okay, suppose there is a Y such that FA and FY and A is distinct from Y. Okay, and now here's an existential. We're going to need to suppose this is satisfied, again, by something new to the proof. So we've now supposed that B, something new to the proof, satisfies this existential statement. And we have this second premise, there is an XGX. We're going to want to start yet another subproof where we suppose something new to the proof satisfies that. So we'll want to suppose GC. Okay, And now we're going to be heading for this conclusion within this subproof and then bringing it out a couple times using existential elimination. So how are we going to get this conclusion within this subproof? Well, presumably we're going to get something that we then use existential introduction on 3 times to get this. We're going to want A is distinct from B, and A is distinct from C, and B is distinct from C. And then we can use existential introduction 3 times to get this, and then existential elimination steps get us to here. So let's figure out how to get this. Note that we already have A is distinct from B as one of the conjuncts in line 5, so we can just pull that out right away. And so now it's just a matter of getting A is distinct from C and B is distinct from C. Okay, well, we have GC, and we know that anything that's G is not F. So we're going to use those 2 pieces of information, right, to get that C is not F. And if C isn't F, then C can't be A and C can't be B because both A and B are F. So that's going to be the key. We're going to start by saying, okay, C cannot be F, can't have the property F because of the 3rd premise here. So let's do that reasoning. And now that we have not FC, that combined with FA and FB is going to get us both of these inequalities. A isn't C and B isn't C, because if we suppose that A is C, for example, we're going to get a contradiction. So if I say, suppose that A is C, I can get FA and FB from line 5, which then gets me FA. And I'm running out of room here, so let me readjust the bottom of this proof to give myself a little more room. Okay, and now that I have FA, I can use the identity A equals C to conclude FC. And in combination with not FC, that gets me absurdity, which then by reductio gets me that A is not identical to C. Okay, so now we've got A isn't identical to B, and A isn't identical to C, so we only need to get B isn't identical to C, and we're going to do that in an exactly similar way, where we would suppose that B is C, and then because we have FB, that would get us FC again, which would contradict not FC, and so we would get absurdity from supposing that B is identical to C, and so we would get B isn't identical to C. We'd have all 3 of our conjuncts. We could use existential introduction 3 times to get this, and then existential elimination once, twice, 3 times to get this, and our proof would be done. So I won't go through writing out all of those steps, but that is how you would complete this proof.